Hi, I'm Aki Vehtari, and this talk is based on the paper which was published in Journal of Machine Learning Research. So whenever you're using Pareto-k, you are using machine learning. So Bob did mention that, 30 draws, that's enough. The sample size is enough, but I'm showing that it's not always enough. So this should be familiar for you. We get draws from the distribution P, theta, and then we can compute these, estimate these expectations with respect to some function h and theta, and we just take the empirical mean. And we know that if this p theta has finite mean, then this estimate, it's consistent and unbiased based on central limit theorem, generalized central limit theorem, and for MCMC, asymptotically unbiased. And if in addition we have finite variance, then central limit theorem tells that variance of this estimate, then we get variance of this distribution and then divided by number of draws. And then we use this to have Monte Carlo standard error estimate. So some estimate how accurate our estimate is, and it's just an like empirical estimate of that variance and then square root of that. And then in the case of MCMC, we use effective sample size, and there's paper about that too. So simple example. These are now exact draws from different distributions, normal denoted by n, and then student t with degrees of freedom 4, 2, 1.5. And here the interesting part is that, so the normal distribution has all moments finite, and then t nu has less than nu fractional moments. I'll come back to why fractional and not just integral moments. So with the normal distribution, this is now cumulative mean, S on x-axis, we get more and more draws, and then the estimated mean gets closer and closer to true, and the variation there gets smaller, and we can then estimate this, like the uncertainty with the normal distribution and with this Monte Carlo standard error. And we can also then look at the squared expectation for the squared quantity, and that converts nicely too. And here 30 draws would be quite good. T4, it has 4 finite moments, so based on these central limit theorems, we get still good behavior for estimating the mean and also for the variance. Student T2, it has finite mean, and the estimate for the mean, converges, but it has infinite variance. And then if we would keep drawing and drawing more, this would never stabilize. It would be just keep drifting around. So no matter how many draws, 30 is not enough. T1 doesn't have finite mean, also known as a Cauchy distribution. So we can't estimate mean, it doesn't exist. No variance. T half, even worse and worse. So what to do? Picons show that many distributions have tail. So if we go far enough in a tail, that this tail is well approximated by generalized Pareto distribution. If we now look at the bulk and tail part, the bulk has compact range, so it has always all finite moments, so we can focus only on the behavior of the tail. So we focus on tail, and then we can fit Pareto distribution, and in this case, for the student T4, the tail is not exactly generalized Pareto distribution, but generalized Pareto distribution with parameter k equal to 1 per 4 matches it well, and you maybe see connection, T4 and K being 1 per 4. And in practice, when we have draws from a distribution, we can use the actual draws and fit the generalized Pareto distribution to those draws, learn from there what is the, that Pareto-k parameter. And so we have this shape parameter k, and then we have 1 per k finite fractional moments. And so we don't care now about the shape of the bulk, but if the tail is long, it's now enough that we know how many finite fractional moments. Repeating with n, now the bottom row is showing estimate for the Pareto-k when we get more and more draws. The dashed line is there, the true value, so for the normal it's 0, and we quite quickly get the estimate being showing that, okay, yeah, everything's good, we have many finite moments. T4, quickly the estimate goes to 1/4. Variation theorem works when we have more than 3 finite moments, even faster convergence to normal. T2, now we didn't have any more finite variance, but we learned with the Pareto-k, it's going to around half, and we know that there might be problems, and so on. For T1, with Pareto-k gets close to 1. For T half, Pareto-k goes close to 2. Now, in this case, these had like no bound how large values we might observe, but this Pareto-k diagnostic works also as pre-asymptotic diagnostic. We may have also thick-tailed but truncated distributions. Like here, I'm taking the T half distribution and truncate it from -8,000 and 8,000. Because it's truncated from both sides, it actually has all finite moments. But when we start getting draws, based on the draws, it looks like we don't see the bounds yet. And what we are estimating behaves just based on what we see so far. It means that before we see the draws at the bound, the estimates for the mean also behave as for this T half distribution. So in the beginning, estimates for the mean and the variance, they are really jumpy. Eventually, when we get enough draws, the estimate stabilize, but also the Pareto-k goes down and below 0, saying that, oh yeah, it's bounded distribution. And in this case, I did show the truncation so that specifically this 10,000 was enough that we started to see the bound. Unfortunately, often the bound is really, really far away, and these kind of thick-tailed distributions are really common in impedance sampling, variational divergence estimation, and so on. And then, or sometimes we have these bounds, but they are really far away. One additional thing is Pareto smoothing, not just diagnostic, but we can also replace now the largest observed, it says ratios, but it should be largest observed values drawn with expected order statistics of that fitted Pareto distribution. Corresponds to modeling of the tail, and usual modeling reduces the noise, so we get better estimate for the mean. A nice thing is also that this Pareto smoothed estimate has finite and mean and variance, even if the original distribution did not have finite variance. The smoothing introduces bias, but it's negligible if the Pareto-k is less than 0.7. What's more, we can also predict the minimum sample size. So this x-axis is k, and y-axis is minimum sample size. Red line is equation I developed, and the blue dots are empirical results. We get what is the minimum sample size needed. Goes much higher than 30. We can also predict convergence rate. Like the usual central limit theorem says that to halve Monte Carlo standard error, we need 4 times bigger S. If we are at Pareto-k 0.7, we need actually 10 times bigger S. And then if the Pareto-k is larger than 1, nothing helps. And so there's the curve and there's equation for that. Okay, now Pareto-k in posterior package. So you can use this, thanks to Noah Kallionen adding the code there. This is first just basic summary. The variables are normal, and then student t with 3, 2.5, 2, 1.51, mean, Monte Carlo standard error. But the Monte Carlo standard error, it's got to be invalid for T1, 1.5 and 2, but this is not telling it. So that's why you need to look at also k-hats. And now the k-hats tell that actually for those where the k-hat is larger than 0.5, the variance is infinite, so the current MSE mean estimates there, they are invalid. You can't use them. We get also minimum sample sizes, but these are now, in the beginning, the minimum sample sizes are for, works also without Pareto smoothing, and the later may require Pareto smoothing. You can see normal, actually 10 is enough. T3, 30, yeah, fine. But then eventually we go to something like 1700. And we get also the convergence rates. So we get how many more draws if we want to have the MSE mean. Now we get also for the student T1 that we would need infinite number of draws. So we know that that's invalid. For the T1.5 and T2, we need to also add Pareto smoothing, but we have functions for that too. And now you can trust all of these Monte Carlo standard error estimates, and then except for this one where we see that we can trust it only with infinite number of draws. In this case, we had more than 1700 draws, so we can trust, and for the others we had enough draws. When to use, to check posterior of any quantity of interest, in high k-hat case, you may then use some other summary than mean. But then, so you could use median, different quantiles, and so on. And then after you check that Monte Carlo standard error estimates are fine, your sample size is fine based on Pareto-k, then you can go check my video case study on how many iterations to run, how many digits to report, then discussing effective sample size and so on. But this is also a very useful insight algorithm that relies on expectations, where other summaries can't be used because the expectation mean is part of the algorithm, and we have the automated diagnostics for those. You don't want to look at every distribution there separately. So there's the QR code for the paper, for the vignette, and there's a bunch of papers where we already use this Pareto-k diagnostic. That's it.
So we have plenty of time for questions, and maybe I'll ask Jesse come down to set up the next speaker.
Be more detailed on what's tail. How do you define when something is a tail? Is it some quantifier? Is it some?
That's a good question. So just a sec, I'll remove this. So in extreme value statistics literature, there are a lot of proposals on how to choose where the tail starts, and there are a lot of also like interactive graphs for that to try to estimate that. In this case, we wanted it to be automated. And then it was partially based on theory, partially like the asymptotic theory, partially other theory, and a lot of computational experiments that we have certain rule, 3 times square root of s, how many draws we take and they are the tail. And then that way it guarantees that if you keep drawing more and more, you will get better and better estimate for the Pareto-k. So there's a problem, like if you include too many draws, you have bias because you are including also bulk. If you include too few, you have high variance. But then this, what we have, seems to work quite well.
What's the recommendation then for non-finite moment like estimates? So not just don't use them? Is that
Like
a
in case, like
or, so yeah, like I mean, so let's say as a user I see this and I'm like, okay, what is like practically then? Should I change to something else or can
yeah,
I
so one possibility is also that maybe you have used too wide priors, maybe you've used COSI prior, maybe you can then consider thinner-tailed prior. If you specifically have information that probably there should not be that much probability mass in the tail. Maybe you started with COSI just because of convenience, and like half COSI used to be a recommendation, not anymore, so it's half normal now. So less likely to see. Sometimes like it really can be that whatever you do, it is really that your quantity of interest happens to have thick tail, but then mean is not useful quantity to report. You want to then report different quantiles. And you want to probably also report that, hey, this tail is really thick. Bob, did you have hand? Yeah.
Yes. Presumably, this isn't an MCMC specific thing, right? Like this would be even if I was doing independent samples from.
So independent directly from the distribution using importance sampling or using MCMC, all fine.
You're questioning the CLT.
When we're estimating the parameter of the generalized Pareto distribution we're fitting, is there a way of diagnosing the inference for the Pareto-k itself?
Yeah, you can get the marginal posterior for the k parameter.
In closed form?
No. So the generalized Pareto distribution has two parameters, scale and the shape. And there's no closed form. So what we are using actually is then profile posterior estimate, which is anyway really close to true posterior, which you can get with the quadrature. But yeah, like you can get fast, like as a side product, you can get the marginal for the k, which is very accurate.
In your experience, this marginal is stable?
Yeah. It's very stable, and then it's really close to the exact or the quadrature solution. And then it gives you then the answer that, okay, I did estimate of like 0.8. What would happen if I get more draws? And then you have the uncertainty, and you could say, oh, actually there's still hope because there's a high probability that it is actually below 0.7, and then you can continue. But if you get like estimate of 3, and the probability that it would be below 0.7, then probably no hope, unless you are hoping that maybe there's a bound, and if you keep drawing enough, you eventually see the bound. But the paper has also example like you need to have more draws than number of atoms in the universe. So yeah.
So suppose I wanted to estimate kind of an expectation that is kind of equivalent to the density of a distribution. So suppose I didn't have the densities in importance sampling, but I would like to, I don't know, approximate it with kernel density estimation or something like that. Would Pareto-k help me figuring out how good my kernel density estimate would be?
Yeah, you can use it if you think of then your kernel density estimate being the proposal distribution, and you get densities from there, you can then compare to actual posterior densities, yeah. Or you could use also then the ECDF envelope, another paper we have, and Teemu and Paul being authors too, yeah.
Let's thank Aki again.